has an Indian origin scientist finally discovered alien life? You must have seen several such reports recently on news channels.
The strongest evidence yet of life. A planet 124 light years away could be home to life. Scientists detected gases in the atmosphere that, on Earth, only come from living organisms.
But is this really true? Doesn't something about this sound off to you? Nikku Madhusudhan is a scientist and an IIT Varanasi graduate who, along with his team at Cambridge University, has discovered a planet called Kepler 21b, where there is a strong possibility of alien life. Now, even great scientists like Stephen Hawking, Enrico Fermi and Nikola Tesla spent their lives waiting for this moment. But haven't such news stories become very common these days? Every year, there are reports claiming that alien life has finally been found, whether it's on planets like Proxima Centauri B, the planets of the TRAPPIST-1 system, or LHS 1140b. And how can we forget Kepler 452, which was even called a super Earth, supposedly even better than Earth for supporting life? But despite all this, the undisputed fact remains that we still haven't found any evidence of alien life to this day. So, is this discovery made by Nikku Madhusudhan on the Kepler 21b planet just another hype? Or has something truly significant happened this time? Well, when I did detailed research on this, I personally confirmed 3 very major discoveries. Discoveries that have never happened before. In fact, we have never even come close to this before. One of these discoveries is that we may have actually found a molecule belonging to alien life. Well, a lot of people can't really tell the difference between hype and reality because they just go by news headlines or YouTubers' opinions. But no one really understands the actual science behind it, which is actually very easy and interesting. And that's why, friends, in this video, I want to find out whether this is fake hype or reality. The answer to this question won't be given by anyone else, but by you yourself at the end of this video. Because I will explain the full picture, the complete science, in the form of a simple story. On March 7, 2009, at exactly 3:49 in the morning, NASA launched the Kepler Space Telescope into space. Instead of being placed in Earth's orbit, it was deployed in the Sun's orbit because this was not going to be an ordinary telescope. Rather, it was designed to look far into the distance and discover planets hundreds of light years away that closely resemble our Earth. And as a result, might have the possibility of alien life. And that's why, so that the Earth doesn't block its vision, it was deployed in the Sun's orbit. From 2009 to 2015, the Kepler Space Telescope stared unblinkingly into the infinite darkness of space to capture some specific movements. This movement was the dimming of light coming from a star, because this could indicate that perhaps a planet passed in front of that star, blocking the light coming from it. And do you know how powerful Kepler is? Imagine if even a fly were to pass in front of the headlights of a car 1,000 kilometers away, Kepler would be able to capture the slight dimming in brightness caused by it. Kepler's eye became the witness. This universe is filled with planets, which exist in numbers far greater than the stars themselves. Whereas earlier, we only knew about a handful of planets. But then, in just 4 years, unfortunately, in 2013, a major mishap occurred with Kepler. 2 out of its 4 reaction wheels failed one after the other. Now, reaction wheels are like the legs of a spacecraft. They help change the telescope's direction and provide it with stability, just like the steering wheel of a car. But without at least 3 reaction wheels, the Kepler telescope couldn't stably point at any single patch of space. And at this point, the mission had almost failed, without having discovered any significant alien planet. But by applying some ingenious thinking, the engineers came up with a brilliant solution. They used the pressure from the sun's rays coming from one direction to achieve stability, just like how a kayak maneuvers in a water current. And with this clever fix, the mission was saved. But this also meant that from then on, the Kepler telescope would only be able to observe a limited area of space. And because of this limitation, NASA redefined its mission in 2014 to focus exclusively on observing red dwarf stars. This new mission was then named the K2 mission, And while previously all discovered planets had Kepler or K in front of their names like Kepler-22b after 2014, the planets discovered were given names starting with K2. K2-18B, the hero planet of our story today, was discovered just a year later in 2015. The telescope detected that this planet was orbiting a red dwarf star, K2-18, completing one revolution every 33 days. And because this planet was the second closest planet to its star, K2-18, it was given the code K2-18B, meaning the second planet from its sun. Now pay close attention, because the story ahead will show you how understanding a planet from as far away as 124 light years can make even scientists break a sweat, and how even major mistakes can happen. So upon studying the initial data sent by Kepler, it was discovered that planet K2-18b is a type of planet that doesn't exist anywhere in our entire solar system. It was called a mini Neptune type planet because its radius is 2.6 times greater than Earth's and its mass is 8.6 times greater. Now, if the size is so huge, then its mass should be 17.6 times more than the Earth. But the mass is only 8.6 times greater. This means its mass was indicating that this planet is made neither mainly of solid rocks like Earth, nor mainly of gas like Jupiter, whose density per square centimeter is extremely low. So what exactly could this light material be? Water. And that's why the leading theory that emerged was that perhaps this planet is wrapped in a vast and deep oceanic layer. But for water to exist in its liquid form, the planet's temperature would have to be above 0 degrees Celsius, right? Otherwise, it would turn into ice. But when factoring in the distance at which K2-18b orbits its red dwarf star and calculating accordingly, the planet's average temperature came out to be -8 degrees Celsius. So unfortunately, did the ice dash our hopes of finding water? Well, you see how a scientist's life is like a roller coaster ride, where they have complete faith that this ride will definitely take them to their destination, no matter how many ups and downs come along the way. And that's why the scientists then thought, what if the planet's atmosphere acts like a blanket and raises K2-18b's temperature above 0 degrees Celsius so that water can remain in a liquid state? But then this meant that it was very important for us to find out what the atmosphere of this planet is like and what it is made of, which was clearly beyond Kepler's capabilities at that time. And that's why entering the picture now is our second hero, Kepler's big brother, Hubble Space Telescope. The Hubble Space Telescope was deployed in space back in 1990. And floating in space, it acts like a giant microscope that can capture detailed, high-resolution images of any space object. But do you know what's most special? Hubble can capture images of those objects in different light spectrums, that is, at various wavelengths. For example, in ultraviolet form, infrared form, and in the form of normal visible light. Okay, so now, how can we possibly know what the thin atmosphere of a planet that's 1,170 trillion kilometers away is made of? Well, get ready to have your mind blown. Look, remember how K2-18b orbits its star every 33 days, right? Now, when it's in front of its star, the star will be shining its light through it from behind. Now, at this moment, if we take a focused and detailed picture of its atmosphere in different wavelengths of light, some parts of the light, meaning some wavelengths, some spectrums reaching the telescope, will have been blocked after colliding with particles in the planet's atmosphere. This happens because atoms and molecules of different elements absorb certain particular wavelengths of light that match their energy levels, based on which we can measure exactly which elements might be present in its atmosphere. For example, here you can see a wave. This is an electromagnetic wave, which is basically the scientific name for light. Yes, light actually travels through space like a wave. But why is the distance between the two peaks of this wave increasing? Well, that's just the nature of light. The distance of its wavelength keeps increasing as the light wave travels longer distances. It's kind of like the light wave gets stretched, and the more it stretches its wavelength, and as a result its energy levels also change. So here you can see that the same light wave starts off in its most powerful form as gamma radiation. Then gradually, as it stretches, it transforms into X-rays, UV rays, visible light, infrared, radio waves, and microwaves. Now pay attention. Each type of radiation has its own wavelength. For example, ultraviolet has a wavelength of 10 to 400 nanometers. Visible light, which we can see, has a wavelength of 400 to 750 nanometers, etc. And for the rest, this is what you can see on the screen. Now, let's say if the atmosphere of K2-18B specifically blocks or dims light at the 589 nanometer wavelength in large amounts, it means that sodium atoms are present there. Because scientists know from quantum mechanics experiments that the energy level of a sodium atom matches the energy level of light at the 589 nanometer wavelength. If the atmosphere blocks or dims ultraviolet light at, let's say, 121.6 nanometers, then hydrogen atoms are present there. 77 nanometers is for potassium, and 1400 nanometers is for water vapor, that is, for water. And the list goes on and on. With this, we can identify the unique fingerprint of every element and molecule. This brilliant method is called transmission spectroscopy, which literally tells us a lot about the composition of a planet even when we are sitting billions of miles away. So, did Hubble succeed? Well, in 2018, Hubble was the first to claim the presence of water vapor, that is, water on this planet, which was a huge discovery. But was the universe really going to reveal its secrets so easily? Hubble's capacity was limited. It could only observe in the infrared frequencies from 1100 to 1700 nanometers. In this frequency range, water vapor molecules closely resemble methane. And that's why, what if what we thought was water was actually just methane gas? Many scientists began to raise such questions, and that's why we soon realized that this data couldn't be trusted. We would need more advanced equipment that could study a much wider spectrum of light so that such measurement errors wouldn't occur. And the stage was set for the launch of humanity's most advanced creation into space, the James Webb Space Telescope. Now, before we find out exactly what secrets the James Webb Telescope has uncovered, let's pause the story here for a moment. Because on the other side, something even more interesting was happening. None other than our Indian origin scientist Nikku and his team had discovered a brilliant concept. Nikku had observed a very interesting thing in the universe. That mini Neptune planets like K2-18B are found in abundance throughout the universe. They are extremely common because red dwarf stars themselves are very common. So why couldn't it be possible that worlds like these also have a chance for alien life to develop? Why are we only focusing on rocky planets like Earth? And then, after studying many such mini Neptunes, Nikku observed some common traits among them. These planets usually have wide, deep oceans, and their atmosphere is covered by a thick layer of hydrogen gas that keeps the planet warm. They even gave such planets a new name, Hycean worlds, combining the words hydrogen and ocean. And according to Nikku Madhusudhan, the K2-18B planet fits perfectly into their Hycean model. Now, according to the Hycean world model, imagine a planet whose atmosphere is dominated by hydrogen and helium. That means at least 80 to 90% of the atmosphere is made up of these gases. Then, in smaller amounts, there can generally be water vapor because of the huge ocean methane, carbon dioxide, carbon monoxide, and ammonia. Now, to validate this model, Nikku's prediction was that in such a world, the amount of ammonia should be extremely low because ammonia is easily absorbed, or rather sinks into water. So just think about it. A world that is filled not with oxygen but with hydrogen. There could be organisms in it that breathe hydrogen, just like some extreme microorganisms on Earth. And because hydrogen is also a greenhouse gas, it can act like a blanket, trapping heat and keeping the ocean water in a liquid state. Here, the oceans could be hundreds or even thousands of kilometers deep. Just imagine how many strange deep-sea creatures exist in our oceans that are only 10 kilometers deep. At depths 100 times greater than that, what kind of alien life could develop under such extreme pressure? But for life to exist, a delicate balance of certain things would be necessary. For example, the layer of hydrogen atmosphere shouldn't be so thick that it turns the planet into something like Venus, which is burning up in its own atmosphere. Or if the ocean is extremely deep, then under such extreme pressure, the water would transform into a special kind of ice halfway down. Ice 6 and Ice 7 are such exotic forms of ice that literally exhibit properties similar to clay. If thick layers of such ice form a barrier between the rocks beneath the ocean and the liquid water, then life wouldn't be able to originate in the same way it did on Earth. It was through hydrothermal vents, that is, underwater volcanoes, that Earth received its first pulse of energy for life. But in such water worlds, there could be many other unique ways for life to originate, which several scientists have actually demonstrated through practical experiments. Dude, take the Miller-Urey experiment from 1952, for example. In that, scientist Stanley Miller literally energized some chemicals with electricity, made them react, and managed to produce 20 organic amino acids. And do you know which elements these were? Well, exactly the same ones that are present in huge quantities on hydrogen worlds: hydrogen, water vapor, and methane. And electricity was used as the energy source, because lightning and thunderstorms are common on planets. So could it be that crackling lightning gave birth to life on this planet as well? Interestingly, scientists have also managed to create components of life's molecules, fragments of RNA, by combining UV rays, hydrogen cyanide, and certain minerals. So there could be many different ways for life to originate. Some of them are even beyond our imagination and knowledge. Now, an important point to note here is that up until now, that is, until 2021, we did not have any confirmed evidence about exactly what the atmosphere of K2-18B is made of. Nikku's team had only created a purely hypothetical model. That is, they used scientific principles to create a simulation of what are the chances of life developing on a planet with such characteristics according to theory. This was important because theory can make predictions, that is, it can forecast exactly what we might find on that planet, which can then be confirmed by advanced telescopes like the James Webb telescope. And if both the theory and the evidence match, it means we are truly seeing the reality. This is the beauty of science. We need both explanation and evidence, theory and proof. So, did K2-18B live up to Nikku's claims? The 8th of January, 2022, the most advanced telescope in history, the James Webb Space Telescope, worth 900 billion rupees, was deployed into space. This space telescope is like the daddy of Hubble. If Hubble is a black and white television, then James Webb is a colored high-definition television. If Hubble can read the half-hidden words of secrets, then James Webb can read entire paragraphs. This is because, remember, Hubble can only observe a very small portion of the infrared light spectrum, roughly from 100 to 2500 nanometers. But James Webb can observe light frequencies ranging from 600 to 28,000 nanometers. Within this wide infrared spectrum, we can not only measure most of the important elements like water, methane, carbon dioxide, ammonia, etc. without any confusion, but we can also detect the presence of even complex biosignatures, that is, evidence of life such as DMS, dimethyl sulfide molecules. Not only that, the light-capturing mirror of the James Webb is almost 2.5 times larger than Hubble's and can capture 6 times more light. But along with that, it is also 100 to 1,000 times more sensitive than Hubble because it operates at an extremely low temperature of minus 233 degrees Celsius. As a result, it doesn't create any electromagnetic noise of its own. That means extremely detailed, high-definition, high-precision, and clear images. If any instrument could provide evidence of alien life, it was this telescope. As soon as it was deployed, the James Webb immediately got to work and mostly since mid-2022 started focusing its gaze on K2-18B. This observation lasted for about a year, and finally in September 2023, the results came out. The James Webb telescope confirmed the presence of methane, carbon dioxide, and yes, even a slight hint of DMS. Now, Nikku and the team just couldn't believe it at first. Because man, this is huge news. Let me explain why. Look, first of all the so-called potentially alien life planets we've found so far, we have not found any evidence of DMS, that is dimethyl sulfide, anywhere. Now, DMS is a molecule that on Earth is produced in measurable amounts only and only no one else only by marine life such as algae and plankton. This chemical is the scent of the sea that we smell whenever we are near the ocean. A sweet, oceanic, cabbage-like and sulfurous smell. Other than DMS, there is no other molecule we know of that can so clearly, without any confusion, indicate that yes, this could be evidence of life. No other molecule even comes close to DMS when it comes to detecting life. Think of it this way. If finding methane is like a whisper in your ear, then finding DMS is like someone shouting in your ear. But it was very important for Nikku to make sure that what they had actually found was DMS and that there was no mistake in the measurement, and that's why Nikku and the team didn't stop here. They had taken the first measurement in the low spectrum of infrared, that is in the range of 800 to 5000 nanometers. Now, to confirm, they decided to measure again in the medium spectrum of infrared, that is in the range of 6000 to 12,000 nanometers. Because if DMS is really present there, it should consistently appear in both the low and medium infrared spectrums. And then, after several months of observations, the final results came in just a few days ago. Once again, the James Webb Telescope has confirmed that yes, DMS or DMD switch is a similar molecule as indeed present in large quantities on K2-18B. How large is the quantity? Well, it's thousands of times more than on Earth, which is huge. Just think about, if Nikku's Hessian model is actually correct, and the real source of DMS there is the presence of alien life, then the entire planet would be filled with massive plant life. Maybe evolution there has given rise to many other types of water-based creatures that we've never seen before. Forget about seeing them, they might even be beyond our imagination. Look, to be honest, we haven't had such a big breakthrough in any alien mission so far. And here there's an extremely solid possibility, a chance, that alien life might actually be developing. But there are still a few more things we need to do before we get to see the climax of the final movie. And they'll have to gather more evidence. And trust me, Nico and his team are probably so excited that they can't even work properly. Because if this discovery turns out to be true, their names will literally go down in history. Look, the James Webb has confirmed the presence of DMS twice, but even now, the evidence we've got has an accuracy that is a precision of 3 sigma level. That means it's 99.7% accurate, but there's still a 0.3% chance that there could be some fluctuations in the signal. And in science, for any major discovery, you need at least 5 sigma level evidence, which means you have to be at least 99.9994% sure that it's correct. And that's why Nico will need a little more time with the James Webb Telescope's measurements to confirm this according to the 5 sigma standard, which in my opinion is now just a formality. But the most important thing we need to be certain about is that apart from life, there really is no other source of DMS on this planet 2-18B. Because the extreme amount of DMS we found, what if there's a completely different source for it that science hasn't understood yet? For example, in some lab experiments, scientists have even produced DMS by exposing molecules like hydrogen sulfide, methane, and carbon dioxide to UV light. So in this case, life wasn't needed at all, right? DMS has even been detected in some comets, no doubt in very small amounts. But on the other hand, Nikku and his team are absolutely confident that according to the Hessian model, K2-18B fits perfectly and there must be life there. There can't be any other source of DMS here because the other sources simply can't produce DMS in such quantities. Even if we do find a non-life source behind this, that in itself would be a major discovery. But because of the very status of this DMS molecule, many scientists are raising the question, can we really rely solely on DMS? Because if there could be any other sources for its creation, then why take even a 1% risk? And finally, there's still one more link left in this unsolved mystery. So far, scientists have found no evidence of ethane in the atmosphere of 2-18B, which is a major missing piece of the puzzle. Because according to the model, wherever DMS is found, its common byproduct, ethane, should also be present in large quantities. But we haven't found ethane yet. This has raised questions about whether our transmission spectrography model itself is incomplete or if the detection was simply inaccurate. So basically, a debate has erupted throughout the entire scientific community, just like it happens with every major discovery. Now, all this confusion will only be cleared up in the next report, in which Nikku and the team will have some important focus areas. Number 1. Confirming the evidence of being DMS at the 5 sigma level. Number 2. Discovering the presence of ethene, which is a byproduct of DMS. Number 3. Maintaining consistency in the non-detection of ammonia. Number 4. Distinguishing between the presence of DMS and DMDS. And finally, number 5. Finding other organic and sulfur-based elements that can clarify whether the source of DMS is life or something else. But do you know what the most serious and important lesson to learn is? Look, the James Webb Telescope isn't just anyone's personal telescope that you can use whenever you feel like it. There is a very robust approval system to use it, which involves long waiting periods. But making a major discovery in science isn't as simple as just pointing a telescope, taking a picture, and revealing the truth. As important as it is to make observations with the telescope, it's even more crucial to refine theoretical, laboratory, and computer models. And all of this work goes on in parallel. We need to understand High-CN models in even greater depth. We have to learn to simulate the atmosphere, climate, and chemistry of those planets in more detail, so that we can understand the intricacies of such planets and make even better predictions. We will have to find other non-biological ways of producing DMS in labs so that we don't end up knocking on the wrong door. And at the same time, apart from the High-CN model, we will also need to create other scientific models that might match the characteristics of K2-18B in an even stronger way. So just imagine, for just one discovery, we have to work in so many different directions simultaneously and face so many failures. In such a situation, don't you think a scientist would get demotivated? Well, absolutely not. In fact, this is exactly what fuels a scientist, their curiosity. Unsolved puzzles, hidden links, secrets gradually being revealed that make you feel like you're on the verge of a major discovery. This is the feeling that every scientist lives for. This is the very nature that makes us feel alive. No matter how dark the path may be, no matter how invisible the destination, the light of curiosity has always led us to our goal. We may be smaller than the dust of the stars, but even so, we possess more fire than they do. Because in this infinite darkness, we are searching for even the faintest spark. Amidst the roar of radiation storms, we are searching for a heartbeat of life. It's possible that this heartbeat may not be of blood like ours, but even so, its echo could change human history. It could rewrite the destinies written in holy books and alter the lines on our palm. And perhaps, by finding them, we might rediscover our lost humanity. Erasing divisions and those who divide, we could unite and together take our civilization to new heights. On the note of unity and peace, this is Gaurav Thakur signing off.